Okay, so this next topic is quite a short one, and we're going to be looking at something called logical operations. And to be able to complete logical operations, we need to be able to draw two truth tables for and or not and exclusive or logical operations. And we need to apply these logical operations to combinations of conditions in programming and package use, in masking, in control systems, and in the use of the exclusive or an encryption. So, first of all, where's my mouse go? Boolean algebra. So we have Boolean values which are true or false, 0 or 1. In the same way that we can add two numbers together and multiply them, true or false values can have operations and or not and exclusive or applied to them. So if we have the and operation, it returns a 1, so true, if both values are true. Otherwise, it returns a false. So if we have a look at a truth table here, so we always have an A, a B, and then the result. So if we have the 0 and a 0, that's a 0 and a 1 is a 0, a 1 and a 0 is a 0, a 1 and a 1 is a 1, because it has to be true and true for it to be true. So for example, if A equals London is the capital of England and B equals cows have wings, okay, we would end up with a false result. Okay, because unfortunately cows don't have wings, or do they? Is it the Red Bull advert that says cows have wings? Anyway, therefore we're saying that London is the capital of England and cows have wings is wrong, and it's a false statement. So we've got or, so it returns true if either values are true. Returns false if both values are false. So if we have the truth table here, if it's false or false, then it has to be false. If it's false or true, then it's true. If it's true or false, then it's true. If it's true or true, then it's true. Okay, so we'll go back to our London is the capital of England, cows have wings statement. We've got A or B, so true or false equals true. So London is the capital of England or cows have wings is true because London is the capital of England. Okay, and then we have exclusive or. So exclusive or is the same as or, but it has a slight difference. Okay, if both values are the same, it returns a false value, but if both values are different, it stays true. So if we have false or false, it's false. False or true is true. True or false is true. True and true is false. So light switches at the bottom and the top of the stairs are an example of an XOR operation. If both switches are off, or both switches are on, then the light is off. But if one's on and one's off, then the light will be on. So not only takes an input and reverses it. So if you say it's not true, then it has to be false. Or sorry, if it's not false, then it has to be true, and if it's not true, it has to be false. Okay, so logical operators in high-level programming. So if we have a look at this here, x equals 7. If x equals 4, then print hello, else print goodbye. If-then statements always have an expression between them, which gives an answer of true or false. So in this expression, x equals 4 is false. Okay, therefore, goodbye is printed. So, if we have a look here, what output would we get from the following? So a equals 3, b equals 7, c equals 5. Okay? If not c greater than 3 and b equals 7, or a greater than 2 and c greater than 8, then print result 1, else print result 2. So what result do you think that we would end up with? Okay, if you just want to pause the video here. Okay, so we need to see if the expression gives true or whether it gives false. So not c greater than 3 and b equals 7, or a greater than 2 and c greater than 8. Okay, so not true and true, or not true and false. Okay, so then that can be simplified to not true or false. Okay, so that then can be reversed to false or false, so the answer is false. Okay, so therefore, result 2 is displayed. Okay, we won't go through this one, it's pretty much the same as the last one, just in more detail. Okay, so logical operations in control. Traditionally, a number of binary digits are used to represent on or off true or false states. These bits are changed using AND, OR, and XOR operations. Each bit of a register or registers is linked, usually via wiring, to a device, for example a heater, a motor, or a light, and if a bit has a 1 entered to it, then it could cause the particular device to be turned on, and a 0 could cause it to be turned off. So, we're going to have a look here at a greenhouse example. Now, there's a lot of examples in the exam spec that basically look at it in terms of a control system rather than just asking you to look at it as a truth table on its own. So a particular greenhouse is controlled by a computer which monitors temperature and humidity and is able to open and close the greenhouse windows, turn on or off a heater, and turn on or off the water sprinklers. So these bits here aren't used, so we can ignore these 5 bits here. So the sprinkler's on if 1, or off if 0. Second bit represents the heater. Third bit represents the windows. So at the moment the windows are open, but the heater's off and the sprinklers are off. Okay, so if we wanted to close the windows and turn off the sprinklers, we'd have to use an AND. Okay, so we've got the AND register here. So all the bits need to be set to 0, and with 0 leave the rest at 1. So if the register was this, okay, and then ANDing would set the register to this. Okay, so we've got 0, 0, 0, 0, and then 1 and a 1 would be true, but a 1 and a 0 is false. Okay, so that would set it so the sprinklers were on. Sorry, the heater was on, but the window's closed. We could also use OR bits to turn the sprinklers on and open the windows. So the OR register, so we could OR the register with the value 101. So if the register was like this, okay, then ORing would set it to this. So because you'd have a 0 or a 1 is a 1, a 1 or a 1 is a 1, and then a 1 or a 1 is a 1. Okay, so then everything will be turned on. Okay, you can also use AND to check the value of a bit, and this is known as masking. And we put masks, as we mask out the bits we're not interested in to look at the important particular bit. So if we wanted to check the sprinklers were on, we would AND the register with the zeros in all positions except the one you wanted to check. If the result is that the value of the register is now 0, then the sprinklers weren't on. Otherwise, they were on. Okay. So using XOR to reverse bits. So it's not particularly relevant in the greenhouse example, but XORing with a 1 reverses the bits. So 0, 0, 0, 0, 1, 1, 1, 1 will reverse the last 4 bits. So if we wanted to use this XOR here, so our little key here to convert it, so we'd have this here, so these bits would stay the same. Okay, and then you would have a 0 and a 1 is true. A 1 and a 1 will be false because they are the same. Okay, again for this one, and then this would return a true value. So XOR has been used for simple encryption in the past. For example, we've got here an encryption key, and we're going to encrypt the word bad. So assuming that this is using the ASCII character set, so B equals 66, C equals 67, D equals 68, A equals 65, and so on. Okay, so we've got bad here. This is how those numbers are represented in binary digits. Okay, so if we want to XOR it with this key here, we would end up with this result because we've got a 0 or a 0 is a 0, 0 or a 1 is a 1, and so on, as you can see all the way down. Okay, so how would we decrypt the coded message? We would just XOR with the same encryption key, and it now acts as a decryption key. So 035, which is the ASCII character set, okay, would then be XOR'd against that key to give us the characters BAD. Okay, this is very similar to something called the Burnham cipher. So if you want to go and have a look into the Burnham cipher in more detail, please feel free to do so. Okay, and that's it for topic 5. It's quite a short video. We will be doing lots of practice in class on truth tables and making sure that we get the technique right for the exam. But apart from that, I'm going to stop the video here.